Hello there, and welcome to Mysteries of Earth. We spend our nights under a dome of familiar lights. Each star appears fixed, ancient, and predictable. For millennia, humanity has trusted the sky to be our constant map, a tapestry where every point of light can be charted, named, and explained. But every so often, the universe reminds us how little we truly know. In late winter of a recent year, while most of us were asleep, an automated survey telescope scanning the heavens for near-Earth asteroids caught something unusual. At first glance, it looked like a faint smudge of light, another anonymous dot among millions. But within hours, its motion betrayed it. This wasn't an ordinary comet, drifting from the frozen outskirts of our own solar system. This was something else, something no one had expected. Imagine a detective poring over surveillance footage and noticing a figure moving against the crowd. That's what astronomers saw when they plotted the new object's path. Instead of looping around the sun on a closed elliptical orbit like all our native comets and asteroids, its trajectory was hyperbolic, an open curve slicing through our solar system from far beyond. It was on a one-way journey, never to return. This was our third confirmed interstellar visitor, a cosmic messenger from a distant neighborhood. Its temporary label, 3I Atlas. Third interstellar, named after the sky survey that first spotted it. A dry designation for a discovery that sent a ripple of excitement and unease through the astronomical community, cut to time-lapse of telescopes slewing. At Harvard's Center for Astrophysics, the alert arrived before dawn. Astronomers there are used to a steady stream of new objects, near-Earth asteroids, comets, space debris. But the words hyperbolic orbit and non-solar origin always make pulses quicken. This wasn't just another rock. This was a traveler from the stars. Why did it matter so much? Because interstellar objects are like bottled messages tossed across the ocean of space. Everything about them, their size, speed, chemical makeup, carries information about the environment in which they formed. Each one is a sample from a planetary system we may never see directly. And until very recently, humanity had seen exactly none of them. Oumuamua, discovered in 2017, had been the first. Borisov, in 2019, the second. And now, scarcely a few years later, a third. The discovery hinted that our solar system might be sitting at the crossroads of a hidden galactic highway, with debris from countless stars streaming past us all the time. If that were true, then each detection wasn't just a curiosity. It was a scientific goldmine. The first images of 3I Atlas were faint and grainy, but enough to reveal something extraordinary. Its brightness suggested a size far greater than either of its predecessors. Oumuamua had been roughly the length of a football field, Borisov perhaps the size of a city block. But this new visitor? Estimates stretched into miles. That scale alone told a story. Small fragments can be flung into interstellar space by gentle gravitational nudges. Medium-sized bodies might be comets, ejected during the chaotic birth of a planetary system. But giants like 3I Atlas? They require violence. Planetary collisions, near misses with massive stars, or perhaps something even stranger. As word spread, telescopes around the world swung toward the newcomer. Observatories in Chile, Hawaii, and the Canary Islands scrambled to adjust schedules. Even the Hubble Space Telescope requested emergency time to capture it before it slipped too close to the sun. Astronomers knew the window of opportunity would be short. Interstellar objects race through our neighborhood like cars speeding down a highway. Blink, and they're gone. zoom in on a comet-like glow. At first, the object seemed inert, just a bright speck moving against background stars. But as it drew closer, sunlight began to wake it. Gases sublimated from its surface, forming a luminous halo and a spectacular tail. Yet the activity levels surpassed anything seen before. This wasn't the modest outgassing of Borisov or the eerie silence of Oumuamua. This was a cosmic light show, pouring out massive clouds of material, visible to even modest backyard telescopes. Harvard scientists watched in awe. Every molecule streaming from the object's nucleus carried chemical clues about an alien world. It was as if a piece of another solar system had drifted to our doorstep, peeling back its layers under the heat of our sun, whispering secrets from its long journey. What secrets? That was the question burning in every mind. Where had it come from? What event had launched it into the interstellar void? And what was it made of? Each interstellar visitor is like an autobiography, written in the language of atoms. The ratios of hydrogen isotopes in its water can reveal the temperature and pressure of the star-forming region where it condensed. The presence of certain organic molecules can tell scientists whether complex chemistry, perhaps even the precursors of life, can arise in distant systems. Heavy elements can hint at how many supernovas had enriched the parent star's neighborhood before the object formed. For Harvard astronomers, the arrival of 3I Atlas was like being handed a pristine, billion-year-old manuscript from another culture and told, "You have a few weeks to read it before it burns." Fade to shots of scientists at computer screens. But there was another reason for urgency and for caution. Oumuamua had confounded expectations, accelerating slightly as it left the inner solar system without any visible jets of gas to peel it. Some researchers had speculated about exotic explanations, from hydrogen icebergs to alien spacecraft. While most agreed on natural origins, the debate showed how little we truly understood about such objects. Atlas, by contrast, was big, bright, and undeniably active. But it, too, carried mysteries. Its path through the solar system was extreme. Its composition, hinted at by early spectra, looked unlike any known comet. And its velocity, faster than both previous visitors, suggested an origin in a region of the galaxy far more turbulent than our own. At Harvard, teams began running simulations. Could such a giant be ejected by ordinary planetary processes? What kind of catastrophe would be needed to launch something miles wide at such speed? Each model raised new questions. The more they probed, the less the object looked like anything predicted. The sense of unease grew. Were we looking at a rare but natural specimen of interstellar debris, or at a category of object we'd never encountered before? And if the galaxy was full of such giants, what else might be traveling the invisible highways between stars, just beyond our detection? Cut to animation of interstellar highways. The concept of galactic traffic might sound poetic, but simulations of stellar motions show it's real. Gravitational currents channel ejected material into streams, much like rivers on Earth. Our solar system happens to sit at the confluence of several. Each time a new interstellar visitor is found, it sharpens the map of these cosmic byways. 3I Atlas wasn't just another comet. It was a probe of the hidden structure of our galaxy. For the first time, astronomers began speaking of interstellar archaeology, the idea that these wanderers are physical samples from other star systems, carrying frozen records of alien chemistry and history. No longer must we infer everything from the faint spectra of exoplanets or the glow of distant stars. Here was matter itself, forged under a foreign sun, now in our grasp. And yet, even with all our telescopes, we could only watch from afar. The object's speed meant no spacecraft could reach it in time. By the time mission planners finished designs, it would be gone, fading back into the black. The frustration was palpable. Each missed opportunity represented lost scientific data, like priceless artifacts dissolving before they could be studied. Music swells. This, then, was the backdrop against which Harvard scientists found themselves staring at their screens. A giant, active, fast-moving enigma from the stars, offering a brief window into a cosmic story billions of years in the making. They had only weeks to capture as much data as possible. The discovery was exhilarating. It was also humbling, because 3I Atlas hinted at something profound, that our solar system is not an isolated island in a silent void, but a busy crossroads where messages from other worlds drift past, unannounced. And if 3 such objects have been found in just a few years, how many have slipped by unnoticed? What larger, stranger things might be traveling those unseen highways, even now, just beyond the reach of our instruments? Fade to black. Voice drops to a whisper as Atlas blazed across the inner solar system. Every telescope on Earth strained to catch its light, every spectrograph to decode its signature. But the real question lingered in the darkness beyond the data. What was this object telling us about the galaxy? And about ourselves? Because perhaps the real story isn't just about a visitor from another star, but about how we, here on Earth, are finally learning to listen. Pause. Music shifts to a subtle, suspenseful theme. And as we trace its path back into the interstellar night, a new mystery begins to unfold. One about the hidden highways of space themselves, and the unseen travelers who may already be on their way. We often imagine interstellar space as a vast empty ocean where stars float like distant islands. Yet hidden within that darkness are travelers, fragments and giants alike, sent forth from alien worlds to wander the galaxy. And every so often, one of these wanderers finds its way to our solar system, arriving like a letter delivered across unimaginable distances. By now, humanity has glimpsed 3 such visitors: Oumuamua, Borisov, and our most recent guest, 3I Atlas. Each arrived carrying unique tales of distant stellar neighborhoods, each whispering secrets that no telescope could ever invent. Together, they form a trio of cosmic ambassadors, a trilogy of interstellar emissaries bearing the chemical and physical imprints of worlds we may never visit. Visual, animation of the 3 objects moving past the sun. The first, Oumuamua, appeared in 2017 like a phantom. It was slender, elongated, a shape unlike anything seen in our own solar system. The light it reflected varied as it tumbled end over end, suggesting a strange cigar-like silhouette. Oumuamua defied classification. It emitted no detectable gases, offered no comet-like tail, and yet subtly accelerated as it left the inner solar system. For a few weeks, scientists debated everything from fractal rock formation to the faintest hints of exotic physics. And while its silence frustrated observers, it spoke volumes about the kinds of bodies that might drift through the galaxy. Small, agile, mysterious. Its story was one of restraint. Oumuamua hinted at environments far from violent upheaval. Its slender shape and modest size suggested that some interstellar fragments might be fragments of collisions, gentle enough to fling them into space without shattering them completely. Or perhaps they were remnants of larger bodies, eroded over eons, drifting alone through the void. The object's unusual acceleration hinted at a delicate dance between light and matter, perhaps shaped by cosmic forces we are only beginning to understand. 2 years later, in 2019, Borisov arrived. A visitor much more familiar, yet no less wondrous. This was a proper comet in every sense, a fuzzy coma enveloping a solid nucleus, a tail streaming elegantly away from the sun, and spectroscopic signals that matched the chemistry we know from our own system. Water vapor, carbon compounds, dust grains, all present, all behaving exactly as theory predicted. But even in its familiarity, Borisov carried alien stories. Its composition reflected the chemical fingerprint of a distant star system, where volatile ices condensed in cold, distant orbits. Its size suggested a body that had been ejected by the violent gravitational interactions of a young planetary system, the cosmic equivalent of being tossed from a cradle too crowded for comfort. Borisov was medium-sized, a cometary diplomat that confirmed the patterns astronomers had long predicted, yet still spoke of a world far beyond our reach. Visual overlay of 3 objects with scale differences. And now comes 3I Atlas, the largest of the 3. Whereas Oumuamua stretched the length of a football field and Borisov spanned roughly a city block, this newcomer measured miles across, a true colossus of interstellar travel. Its size alone tells a tale of a violent origin, a planetary system capable of flinging massive objects across the galaxy at tremendous velocities. We can read these 3 visitors like a series of geological layers, each revealing conditions in alien stellar nurseries. Small objects like Oumuamua hint at gentle ejection mechanisms and long survival in isolation. Medium-sized comets like Borisov tell of young systems full of turbulence and scattering. Giants like 3I Atlas require extraordinary events. Collisions between massive worlds, gravitational encounters with giant stars, or perhaps something we have yet to imagine, cut to simulated spectra of each object. Beyond size and shape, the chemistry of these wanderers adds richness to the story. Oumuamua, largely inert, offered few direct clues about composition, though its mysterious acceleration suggested it might release minute quantities of gas undetectable by current instruments. Borisov, meanwhile, displayed sublimation of familiar ices, revealing water, carbon monoxide, and various organic molecules locked in a deep freeze for millions of years. Atlas, in contrast, exploded into activity. Gases and dust clouds poured from its surface, visible to telescopes worldwide. Its spectrum showed familiar molecules: water, carbon compounds, silicate dust, but in quantities far greater than anything previously seen. Isotopic analysis hinted at conditions in its parent system. The ratio of heavy to light hydrogen in water molecules suggested formation in a cold, distant environment. Organic compounds indicated chemical processes over geological timescales, implying a stable planetary system capable of fostering complex chemistry. Every photon captured from these objects is like reading a letter from another civilization, not of beings, perhaps, but of worlds. Oumuamua whispered secrets about isolated fragments drifting through space. Borisov offered the orderly narrative of a young system with predictable chemistry, and 3I Atlas broadcast the drama of a cataclysmic past, violence, heat, and chemical richness encoded in its massive glowing core. Visual, animation of velocity vectors. Speed adds another dimension to the comparison. Oumuamua's velocity suggested origins in a local stellar neighborhood, relatively calm and close. Borisov's path hinted at a system somewhat farther away, while 3I Atlas raced past the sun with extreme speed, implying ejection from a particularly chaotic region of the Milky Way. Each velocity, n combined with trajectory and chemical data, becomes a clue in the cosmic puzzle. From this, astronomers can begin to reconstruct the circumstances that launched these objects on their journeys, tracing them back across the galaxy as if following breadcrumbs left over billions of years. Visual, telescopes around the world observing. Observational differences also shape the story. Oumuamua's inert nature demanded patience, subtle measurements, and careful modeling. Borisov's moderate activity allowed direct study of gas emissions and dust dynamics. 3I Atlas, by contrast, required a global mobilization, telescopes in every hemisphere coordinating schedules, rapid response campaigns to catch fleeting outbursts, and spectrographs trained to capture every molecule before it drifted beyond detection. In many ways, these three objects reflect humanity's own journey in understanding the cosmos. From the first enigmatic detection of Oumuamua, requiring deduction and theory to interpret sparse data, to the more straightforward analysis of Borisov, to the frantic global scramble to study 3I Atlas, each discovery has pushed the boundaries of observational astronomy. Yet beyond the science lies a profound philosophical insight. Each visitor is a reminder that our solar system is not isolated. Invisible highways crisscross the Milky Way, carrying material from one star system to another. Small fragments, medium comets, and colossal giants all navigate these routes, creating connections we are only beginning to perceive. In this sense, Oumuamua, Borisov, and 3I Atlas are not just isolated oddities. They are part of a broader galactic traffic system, linking worlds through space and time. Consider it like finding artifacts from three distinct civilizations, one modest and enigmatic, another familiar but foreign, and a third, colossal and awe-inspiring. Together, they reveal the diversity of the universe, hinting at processes both gentle and violent, ordinary and extraordinary. Each tells us something unique about alien environments, the conditions under which planetary systems form, and the challenges faced by objects venturing across light years to reach us. Perhaps the most striking lesson is humility. The galaxy is vast, its highways invisible, its messengers fleeting. What we have discovered so far represents only a fraction of what passes by our solar system unnoticed. Every interstellar object is a direct sample from another world. Yet even with all our technology, we have only glimpsed a few. Imagine the countless stories drifting in the dark, forever beyond our reach. And yet, the three we have studied, Oumuamua, Borisov, and 3I Atlas, offer a tantalizing window. Through them, we can begin to compare alien worlds, reconstruct histories of distant stars, and understand how planetary systems differ across the galaxy. Each is a chapter in a narrative of interstellar migration, a testament to the dynamic and interconnected nature of the cosmos. As we finish tracing the journeys of these three wanderers, the question emerges: what comes next? What other giants, emissaries, or silent fragments might be approaching, waiting to carry more secrets across the cosmic void? Because the story of interstellar visitors is not merely the story of isolated objects. It is a story of a galaxy alive with motion, exchange, and chemical complexity. And we, for the first time, are beginning to read its messages. When it comes to interstellar visitors, size is more than a simple measurement. It is a story etched in cosmic forces, a silent biography written in the language of physics. Imagine three wanderers, each crossing the gulf between stars: Oumuamua, Borisov, and our newest colossal visitor. Their differences in scale are staggering, and they hint at the dramatic circumstances that flung them from their home systems into the dark reaches of our galaxy. Oumuamua, discovered in 2017, was roughly the length of a football field, slender and elongated, drifting silently through space. Its modest size meant that the gravitational nudge needed to escape its parent system could be subtle: a glancing blow from a passing planet, a gentle tug from a distant star. Yet even this seemingly small object carried secrets, a story encoded in its motion, shape, and surface, whispering of distant stellar neighborhoods we may never directly observe. Borisov, arriving 2 years later, was larger, closer in scale to a city block. Its dimensions suggested a more substantial launch event. Perhaps a young planetary system, chaotic and unsettled, scattered leftover material during the final stages of planet formation, ejecting pieces of ice and rock into interstellar space. Borisov behaved like a textbook comet, displaying a fuzzy coma and a tail that streamed like smoke in the cosmic wind, confirming theories of how objects born around alien suns might journey through the void. Its very existence told astronomers that interstellar objects could carry familiar chemistry, familiar behaviors, but still represent wholly alien worlds. Then came our newest visitor, a giant, a leviathan among wanderers. Miles in scale rather than hundreds of feet, it dwarfed both Oumuamua and Borisov. To hurl something this massive from a stellar system requires violence on a scale almost unimaginable. Ordinary planet, RE tugs, or gentle gravitational nudges simply would not suffice. This object must have been cast out during catastrophic events: a close encounter with a binary star pair, the slingshot from a massive planet, or even the chaotic upheaval of a star system destabilized by a passing rogue body. Its size alone hints at a narrative of destruction and escape, a cosmic drama frozen in the tracks of its trajectory. Consider the physics behind these interstellar journeys. Accelerating a small rock the size of Oumuamua to escape velocity is possible with a single, well-timed encounter. But with objects measured in miles, like our current visitor, energy requirements skyrocket exponentially. It is the celestial equivalent of throwing a mountain across the galaxy. Yet here it is, surviving the million-year voyage through interstellar cold, radiation, and the constant bombardment of micrometeoroids. Its mere presence raises questions. What forces could have produced such an object? And what kind of system did it originate from? Size also reveals survival strategy. Smaller objects with low mass may be more easily altered by radiation or erosion in interstellar space. Their surfaces can become pitted, scorched, and chemically transformed. Larger objects, in contrast, carry protective insulation. Thick mantles of ice and dust shield the interior from the harshest effects of cosmic rays and particle bombardment. Our massive visitor shows evidence of such preservation. The outer layers have weathered interstellar time, but beneath, Materials remain frozen, pristine, a record of alien chemistry untouched for millions of years. In essence, its size has been a survival mechanism, allowing it to arrive in our solar system relatively intact. The differences in size also suggest diversity in the mechanisms of ejection. Oumuamua's slender body may have been a fragment torn from a larger parent, chipped off during planetary collisions or gravitational interactions. Borisov, more massive and comet-like, may have formed in a dense debris disk, gradually nudged into escape by the combined pull of planetary neighbors. Our newest giant, however, implies events that are rare, extreme, and violent. Only a system with massive planets, chaotic orbital resonances, or unusual stellar dynamics could launch such a heavyweight into the galaxy. It is a messenger not only of chemistry, but of stellar architecture and the violent evolution of planetary systems. These size disparities also allow astronomers to piece together the hidden demographics of interstellar wanderers. Small objects may be plentiful, but hard to detect until they venture close to a star. Medium objects like Borisov are rarer, but more readily observed. Giants are exceptional, striking phenomena that demand attention simply by their visibility. Observational biases mean we have likely glimpsed only a fraction of the interstellar traffic passing through our neighborhood, and size plays a critical role in determining which objects we see. For every Oumuamua, dozens may slip by unnoticed. For every Borisov, 100 more may pass in silence. The giants, though few, are the heralds, impossible to ignore, and their dramatic displays give humanity the rare chance to study distant chemistry at close quarters. Size also impacts the narrative of interstellar chemistry. The more massive an object, the more diverse its material inventory can be. A small fragment may contain a limited array of compounds, stripped by collisions or thermal processes. A larger body, however, acts like a repository, preserving layers of ice and rock that record different epochs of its origin system. Solar heating, as it nears our sun, exposes these layers in succession, creating a temporal map of chemical history. In the case of our massive visitor, the combination of ice, dust, and organics hints at a complex origin, possibly around a mature star that allowed chemical processes to evolve over millions of years. Yet size is not only a measure of survival or chemical storage. It also shapes the journey itself. Smaller objects are more susceptible to gravitational perturbations during encounters with stars or planets. They are deflected easily, their paths altered with minimal energy exchange. Larger objects, by contrast, possess the momentum to resist minor gravitational nudges, preserving the integrity of their trajectory over millions of years. The interstellar highways they traverse are therefore partly determined by mass, with larger bodies following straighter, less disrupted paths. Our giant visitor's precise hyperbolic trajectory suggests it emerged from a system capable of imparting enormous energy, launching it on a relatively unbroken course across the galaxy. Comparing the three wanderers as a group, a pattern emerges. Size, velocity, and behavior are intertwined threads, revealing the hidden architecture of interstellar motion. Oumuamua whispers of subtle, local interactions. Borisov tells of planetary systems undergoing the standard process of comet ejection. Our massive visitor speaks of extraordinary, possibly catastrophic events, hinting at environments far removed from the calm, stable neighborhoods where stars like our sun reside. Collectively, they provide a window into the diversity of planetary systems and the spectrum of forces capable of creating interstellar travelers. Perhaps most astonishing is the realization that size directly informs what we can learn about alien worlds. Small fragments like Oumuamua allow insight into surface chemistry and shape, offering clues about collisional histories. Medium comets like Borisov expose volatiles and dust behavior under solar heating, revealing the physics of icy bodies beyond our system. And massive visitors carry deep reservoirs of primordial material, a layered record of distant star systems preserved in frozen time. The larger the object, the more expansive the library of interstellar knowledge it delivers to our doorstep. In contemplating these three visitors, we begin to appreciate the choreography of forces at play: gravity, radiation, orbital dynamics, and chemical preservation, all woven together. The size of each wanderer is a signature of both its origin and its journey, a cosmic fingerprint that tells us not only where it came from, but how it survived the void for millions of years. The differences among them illustrate that interstellar space is not a uniform wilderness, but a complex arena where objects of all shapes and scales navigate invisible highways, carrying information about distant stars, planetary systems, and cosmic events. And as we in the darkness between the stars, behavior becomes a signal, a story written not in words, but in motion, light, and chemistry. Observing interstellar visitors is like watching alien lives unfold from millions of miles away, each revealing secrets about their home systems, their composition, and the extraordinary journeys they have endured. Among the three wanderers that have visited our solar system, behavioral differences are not minor details. They are windows into the physics, chemistry, and history of distant worlds. Oumuamua, the first interstellar visitor ever detected, entered our system almost silently. It glided past the sun with minimal fuss, displaying none of the visible signs we associate with comets or asteroids. No coma, no tail, no plume of gas or dust. Its elongated shape twisted through space, reflecting sunlight in unusual patterns, but it refused to act like any object familiar to astronomers. Here was a traveler that seemed almost deliberate in its secrecy, carrying its secrets close. What could this silence mean? Perhaps Oumuamua had exhausted its volatiles long before it reached us, its icy reserves sublimated into nothingness across the millions of years spent in interstellar cold. Or maybe it was a fragment of a larger object, stripped down to rock and metal, leaving no ice to boil into a glowing halo. Its behavior, or lack thereof, challenged astronomers' assumptions about what interstellar objects should be. Every time Oumuamua passed into a new observational window, it offered hints, yet refused to yield a full story. The stillness of this visitor made every measurement precious. Every photon captured a rare glimpse into a distant system's quiet, enduring remnants. Borisov, in contrast, entered like a textbook example of what astronomers had long expected of an alien comet. Its nucleus, though small in cosmic terms, carried frozen reservoirs of gas and dust. As it approached the sun, these ices sublimated, forming a coma of shimmering particles and a tail that streamed elegantly away from the solar wind. Spectroscopic studies revealed familiar chemicals: water, carbon monoxide, carbon dioxide, and traces of more complex organics. Borisov's behavior confirmed decades of theoretical models, showing that interstellar comets could behave very much like those formed in our own solar system, despite originating light years away. Yet the charm of Borisov lay not only in its predictability, but in the window it offered into a living alien system. Its eruptions, the steady release of gas and dust, acted like messages sent across the void. They told astronomers about temperature gradients in its interior, the layering of ices and dust, and the physical structure of its nucleus. It was as if a distant star system had entrusted us with a fragment of its chemistry, carefully preserved and now unveiled in the sunlight of our solar system. By contrast, Oumuamua's silence seemed almost defiant, a riddle wrapped in cosmic shadows. Then came the newest visitor, Three-Eye Atlas, a spectacle of motion and light, unlike anything seen before. Unlike Oumuamua's silence or Borisov's steady activity, this giant erupted into brilliance as it approached the sun, massive clouds of sublimating material, illuminated by sunlight, created a transient display visible even to smaller telescopes on Earth. Its behavior was dramatic, a vivid performance in the vast darkness, drawing the attention of professional and amateur astronomers alike. The eruption of 3I Atlas revealed more than spectacle. It revealed the forces at work within this enormous body. As the sun's heat penetrated its surface, layers of ice and volatile compounds began to sublimate, ejecting dust and gas into space. Jets of material erupted from the nucleus, sending plumes thousands of miles across the void. Observatories tracked the changes in brightness, mapping the evolving coma and capturing the dynamic evolution of this extraordinary visitor. In every outburst lay a story of chemistry, of layers preserved over millions of years, now exposed to the warmth of a distant star. Behavior also carries clues about internal structure. Oumuamua's silence suggests a dense, perhaps compact body, with little to no volatile material remaining. Borisov's steady outgassing indicates a porous, ice-rich nucleus, capable of gradual sublimation without catastrophic breakup. 3I Atlas, by contrast, demonstrates an active and possibly unstable interior, where pressures built up over time are released in bursts of material. By comparing these behaviors, astronomers can begin to classify interstellar objects not just by size or trajectory, but by the stories their motion tells. Velocity and trajectory intersect with behavior in revealing ways. Oumuamua's modest acceleration suggested subtle forces at work, possibly hinting at outgassing too faint to detect or a shape so unusual that solar radiation itself affected its motion. Borisov's acceleration and tail aligned predictably with solar heating, confirming models of cometary physics. 3I Atlas's dramatic eruptions, however, introduced new questions. How could a body of this scale release material so rapidly without disintegrating? The answer lay in internal heat, perhaps accumulated over millennia, and in structural features capable of channeling pressure until explosive release. The timing of activi. Even the chemical signatures of outgassing provide behavioral clues. Borisov's well-behaved sublimation revealed the presence of simple compounds and organic molecules, confirming formation in a cold, stable region around its parent star. 3I Atlas's eruptions, in contrast, released an unusually rich mixture of gases, hinting at complex layering of materials and potentially exotic chemistry that may never have experienced the same homogenizing forces that shaped our own comets. Through these patterns, behavior becomes a lens into alien environments. What temperatures were reached, what pressures shaped the interior, and what chemistry could survive the long voyage between stars. The differences in behavior also underscore the importance of observational timing. Oumuamua passed swiftly through our solar system, silent and unyielding, giving scientists only brief windows to study its unusual motion. Borisov offered a more extended and predictable opportunity, allowing continuous monitoring of its activity and composition. 3I Atlas, by erupting dramatically, created an observational bonanza. Though fleeting, the eruptions allowed the collection of large quantities of spectroscopic data in a very short time. For astronomers, behavior dictated both opportunity and challenge. The more dynamic the visitor, the more data could be captured, but the faster conditions could change. Behavior, ultimately, is a key to understanding origin as well. Oumuamua's silent passage suggests either an old, depleted system or a fragment stripped of volatiles during ejection. Borisov's classical activity hints at a relatively young system still rich in ices and dust, with ejection occurring during planet formation. 3I Atlas, by contrast, hints at a violent origin, perhaps ejected during catastrophic events in a mature system where chemical diversity had time to evolve. Each behavior is a fingerprint, unique to the object's history, environment, and the forces that set it on its journey. Beyond scientific significance, these behavioral differences ignite the imagination. Oumuamua's quiet glide invites speculation about alien worlds and mysterious processes beyond our reach. Borisov's familiar patterns reassure us that the physics of our own solar system extends into the galaxy. Three-Eye Atlas's spectacular eruptions remind us that the cosmos is capable of dramatic surprises, that interstellar travelers can appear with theatrical grandeur, and that each visitor carries stories both expected and entirely unforeseen. In contemplating these three wanderers, we see behavior as a narrative. Motion, outgassing, and eruptions become sentences in a larger story about distant stars, chemical evolution, and cosmic violence. The silent, the predictable, and the spectacular each convey unique insights, revealing what compositions, structures, and histories might lie hidden in the interstellar void. Astronomers read these behaviors like letters from another galaxy, decoding information not only about the objects themselves, but about the broader mechanisms at work in alien planetary systems. And as Three-Eye Atlas continues its luminous display, we are reminded that interstellar visitors are not merely objects. They are living archives of motion and chemistry, emissaries carrying dynamic records across unimaginable distances. Their behavior is a key that unlocks understanding, offering glimpses into environments and events that shaped planets, stars, and perhaps even the building blocks of life far beyond our own solar system. The velocity of an interstellar visitor is more than a number. It is a signature, a clue etched into motion across the vast emptiness of space, whispering the story of its origins. When astronomers first tracked Oumuamua, its relatively modest speed suggested that it had not traveled from the far reaches of the galaxy, but from a nearby stellar neighborhood. Its path was subtle, almost familiar, hinting that it had been nudged gently from the outskirts of a nearby system and sent on a long, quiet voyage. Comet Borisov, by contrast, raced past at an intermediate velocity. Its trajectory carried it from farther afield, a wanderer ejected from a planetary system, more distant, more tumultuous. The path it traced through our solar system reflected the gravitational choreography of multiple stars, the lingering influences of unseen planets, and the push and pull of galactic tides over millions of years. Each acceleration, each deviation, became a breadcrumb, revealing the invisible hands that shaped its journey. Then came Three-Eye Atlas, a true giant on the move, traveling at speeds that defied simple explanation. Its velocity suggested origins in a violent stellar environment, a region where gravitational encounters and cosmic upheaval are the norm rather than the exception. To achieve such speed, a tremendous force must have acted upon it. Planetary collisions, the gravitational slingshot of massive stars, or even the cataclysmic death of a nearby star. The object's rapid approach illuminated a hidden truth. The galaxy is not a random scatter of isolated stars, but a network of motion and momentum, a cosmic web along which matter flows. Astronomers now recognize that interstellar objects are not drifting aimlessly. They follow invisible highways, paths carved over eons by the gravity of stars, clusters, and the spiral arms of the Milky Way. Like rivers flowing through a landscape, these traffic lanes guide debris from planetary systems far beyond our reach toward others, occasionally delivering fragments to our own solar system. Every object that arrives carries a record of these paths, a testament to the forces shaping the interstellar medium. Mapping these highways requires more than a single observation. Scientists must calculate not just current velocities, but project millions of years of motion, accounting for the drift of stars through the galaxy. Stars are not fixed points in the night. They orbit, collide, and cluster, altering the flow of interstellar material. A comet ejected today from a distant system may take tens of millions of years to reach another, weaving through a gravitational maze whose architecture is only beginning to be understood. Velocity also encodes the story of ejection. Small, compact objects like Oumuamua require relatively little energy to escape their parent stars. They may be fragments knocked loose by gentle gravitational nudges, wandering through space over millennia without dramatic force. Borisov-sized comets demand stronger events, planetary formation processes that eject ice and dust into interstellar space. Giants like 3I Atlas imply catastrophic events, violent processes that can hurl enormous masses across the galaxy at extraordinary speed. Each speed is a clue, each trajectory a fingerprint of the conditions that once prevailed in distant stellar nurseries. These invisible highways are not uniform. Certain regions are more heavily trafficked, shaped by binary star systems, dense stellar clusters, and gravitational resonances. Planetary systems near chaotic environments are more likely to eject debris, filling interstellar lanes with fragments of rock, ice, and frozen organics. Conversely, isolated stars in calm regions contribute far less. The galaxy is a city of roads, boulevards, and side streets, where objects follow predetermined paths, often unseen, yet dictated by the invisible architecture of gravity. Interstellar visitors arriving at Earth are the rare intersections of these highways with our own solar system. Each discovery is a fleeting glimpse of this dynamic network, a confirmation that our neighborhood is part of a larger, interconnected cosmic environment. By analyzing velocity and trajectory, astronomers can trace these visitors backward, reconstructing the routes they have traveled and hypothesizing about the stars that once nurtured them. Every measurement of speed reveals more than motion. It hints at the history of encounters with other stars, the gravitational perturbations that nudged an object along its route, and the time it has spent in the cold, dark void of space. The interstellar medium, once thought of as largely empty, becomes a complex highway system, its lanes invisible yet defined by physics, guiding travelers from star to star across unimaginable distances. These cosmic highways also shape our expectations for discovery. By understanding where ejected material is likely to travel, astronomers can predict the directions from which the next interstellar visitor may appear. Survey telescopes can be aimed not randomly, but strategically, aligned with the most probable intersections of these gravitational lanes. In essence, mapping velocity and trajectory is akin to charting the traffic of a vast, invisible city, where each object offers insight into the routes, congestion points, and intersections that govern galactic motion. Velocity, trajectory, and gravitational context together transform the study of interstellar visitors from mere observation to storytelling. Oumuamua tells a tale of a quiet nearby ejection. Borisov narrates a more distant journey, moderated by the subtle chaos of its stellar birthplace. 3I Atlas blazes a story of power, of forceful launch, and of interstellar highways that carry massive objects across millions of light years. Through these differing speeds, astronomers begin to understand the invisible infrastructure of our galaxy, a network that shapes the movement of matter, the flow of history, and the delivery of alien fragments to our doorstep. The concept of cosmic highways challenges the old notion of stars as isolated islands. Our solar system is not alone, but part of an intricate galactic web, connected through the paths of wandering comets and asteroids. These objects are not random visitors. They are messengers traveling along well-defined channels, offering chemical, structural, and dynamical information about their origins. Every calculation of velocity and trajectory is a key to decoding these hidden routes, revealing the interconnectivity of the Milky Way. In contemplating these invisible pathways, one begins to see the galaxy as an ecosystem of motion, where stars, planets, and the debris they generate interact across vast scales. Interstellar objects are the traces left behind by these interactions, physical letters written in velocity and orbit, delivered across time and space. By tracking their motion, we gain insight not only into the visitors themselves, but into the broader cosmic network that orchestrates their journey. Velocity is more than a measurement. It is a storyteller. Every acceleration, every deviation, every rapid approach or leisurely drift encodes chapters of interstellar history. By studying these cosmic travelers, we are not merely observing objects in motion. We are reading the movement of matter across the Milky Way, tracing the invisible highways that link distant stars, and understanding the dynamics that shape the flow of the galaxy itself. Every interstellar visitor carries a story, but 3I Atlas speaks in the language of atoms. Beyond its luminous tail and rapid motion lies a hidden autobiography, written in the chemistry of its ices, gases, and dust. Spectroscopy, the art of reading light, allows astronomers to translate that story, revealing the intimate details of the star system that once nurtured this cosmic wanderer. The first words in this chemical autobiography are written in water, but not the ordinary water we know on Earth. The isotopic composition, ratios of heavy to light hydrogen atoms, offers a direct message from its parent system. Variations in these ratios encode the temperature and pressure conditions that existed when 3I Atlas's ice first formed. Subtle shifts, detectable only through careful measurement, are fingerprints of the stellar nursery that shaped it billions of miles away. By comparing these isotopes to those found in comets of our own solar system, scientists can begin to draw parallels and contrasts between alien and familiar environments, asking questions about how planetary systems evolve under different cosmic conditions. Next come the carbon compounds, abundant and varied. Spectroscopic signatures reveal carbon monoxide, carbon dioxide, and complex organic molecules locked within the nucleus. Each molecule is a sentence in a long chemical tale. These compounds suggest formation in regions where carbon chemistry could flourish, perhaps within the cold outskirts of a protoplanetary disk, or amidst the scattered debris of a young planetary system. Some of these organics are remarkably fragile, yet they have endured the deep freeze of interstellar space for millions of years, carried across light years of vacuum as pristine messengers from a distant star. But carbon tells only part of the story. The presence of heavier elements, magnesium, iron, and other metals, offers insight into the generational history of the parent star. These elements are the echoes of previous stellar explosions, supernovae that seeded the interstellar medium with material later incorporated into 3I Atlas. In essence, each atom of metal is a relic of cosmic ancestry, a breadcrumb linking this visitor to the cycles of birth and death that govern the galaxy. It is a chemical family tree written across the periodic table. What makes these discoveries remarkable is not just the presence of individual compounds, but the interactions between them. Some molecules bear the marks of cosmic radiation, transformed into daughter products that record the length and conditions of the interstellar journey. These chemical timestamps allow astronomers to reconstruct not only the birthplace of 3I Atlas, but also the story of its passage through the void, the bombardment of high-energy particles, the exposure to ultraviolet radiation, the slow sublimation of ices that marks its approach to our sun. Every layer of the nucleus is a frozen archive. The outermost ices, exposed to sunlight for the first time in millions of years, reveal volatile compounds that ignite spectacular activity. Beneath them lie more pristine layers, shielded from radiation and preserved in cosmic time. Probing these depths remotely through spectroscopy allows scientists to read the chronology of formation and evolution, like examining tree rings or ice cores that record epochs of environmental change. Some of the organic molecules detected are particularly tantalizing. They hint at chemical processes akin to those that may have occurred in the early solar system, suggesting that life's building blocks are not unique to our corner of the galaxy. The conditions needed to form such compounds, stable temperatures, protection from destructive radiation, and time for complex reactions, tell us that the parent system of 3I Atlas was mature, stable, and chemically active for extended periods. This was not debris flung from a chaotic newborn star, but material forged in a seasoned environment, capable of nurturing chemical complexity over millions of years. Spectroscopy also allows for the mapping of temporal changes. As 3I Atlas approached the Sun, its increasing activity revealed which compounds were buried deep and which were already at the surface. Outgassing patterns, brightness variations, and emission lines from molecules provided a dynamic portrait of the nucleus, showing how the object responded to solar heating and how different chemicals sublimated at varying distances. Every observation became a piece of a larger puzzle, revealing the interplay between structure, composition, and environment. The implications extend far beyond mere chemical cataloging. Each detected molecule, each isotopic ratio, is evidence of planetary processes in an alien system. The formation of ice, the accumulation of dust, the aggregation of rock and volatile material. In a way, 3I Atlas acts as a sample return mission from an impossible distance, delivering intact material for study without ever leaving its trajectory through space. By decoding its spectral fingerprints, we gain direct insight into the building blocks that shaped worlds light years away. Even the most subtle spectral signatures matter. The presence of specific isotopes or trace molecules can indicate temperature gradients in the protoplanetary disk, variations in radiation exposure, and chemical reactions over vast periods of time. These details provide astronomers with a nuanced picture of the parent star's environment and hint at the diversity of planetary formation across the galaxy. The chemical autobiography of 3I Atlas, read through light across the electromagnetic spectrum, transforms the object from a simple visitor into a messenger, carrying tangible evidence from a distant world. Each photon captured is a line of text, every emission line a paragraph, collectively telling the story of a system we may never visit directly. By interpreting these chemical messages, humanity gains access to the inner workings of planetary systems beyond our own, observing processes that unfold on scales both vast and minute. Through water isotopes, carbon chemistry, and metallic content, we glimpse the conditions of a distant star system. The heat of its early days, the stability of its maturity, and the violent forces that eventually ejected 3I Atlas into interstellar space. The visitor is both archive and messenger, a physical testament to processes we have long theorized but rarely witnessed in such pristine form. In this way, spectroscopy turns the cosmos into a laboratory. We read the autobiography of alien matter without touching it, decoding chemical letters written long before Earth had oceans, continents, or life. 3I Atlas offers proof that the processes shaping planets, creating organic molecules, and distributing material across the galaxy are universal, governed by the same laws of physics and chemistry that operate in our own solar system. By following these chemical trails, astronomers can not only reconstruct the history of 3I Atlas, but also begin to understand the broader network of interstellar material that connects stars and planetary systems. Each spectral analysis is a bridge, linking our understanding of nearby comets to the distant reaches of the Milky Way, and reminding us that the galaxy is a shared laboratory of formation, evolution, and chemical storytelling. The moment 3I, our Atlas, was confirmed as an interstellar visitor, the clock began to tick. Not in years, months, or even weeks, but in days and hours. Its trajectory was taking it ever closer to the sun, racing toward a point where it would vanish behind solar glare, invisible to our eyes and instruments. What followed was nothing short of a cosmic emergency, a global scramble to capture every photon before this celestial messenger slipped beyond reach. Astronomers at professional observatories felt the weight immediately. The Hubble Space Telescope, normally booked years in advance for distant galaxies and exoplanet studies, received emergency observing time. Teams worked frantically to reconfigure instruments, adjusting cameras, spectrographs, and scheduling windows with precision. Every second counted. Missed exposures could mean the loss of rare spectroscopic data, the disappearance of subtle outgassing patterns, and the erasure of fleeting events that revealed the object's internal structure. But it wasn't only the realm of professionals. Amateur astronomers, equipped with increasingly sophisticated CCD cameras and access to global telescope networks, became vital participants in the campaign. From backyard observatories under clear skies in rural Chile to rooftop setups in urban Europe, citizen scientists provided continuous coverage as the Earth rotated. While large observatories were limited by scheduling and atmospheric conditions, the global web of amateurs filled in the gaps, capturing data that might otherwise have been lost. Their contributions weren't just supplemental, they became essential pieces in the larger scientific puzzle. Coordinating this effort resembled an intricate relay race. Observatories across continents communicated constantly, sharing preliminary measurements, adjusting observing schedules, and cross-checking brightness variations. Infrared telescopes measured heat emissions from the nucleus, mapping temperature changes as sunlight penetrated the icy surface. Optical instruments tracked minute variations in brightness and motion against a backdrop of distant stars. Radio dishes scanned for molecular emission lines that could reveal the precise chemical makeup of sublimating gases. Each facility, each instrument, was a link in a chain, collectively constructing a dynamic portrait of an object moving at extraordinary speeds through the solar system. Time pressure added another layer of complexity. As 3I Atlas approached solar conjunction, the geometry of observation shifted constantly. Angles between the Sun, Earth, and the comet altered lighting conditions, visibility, and the ability to detect specific features. Some observations were only possible during narrow windows, lasting mere hours before the object's motion and the planet's orbit rendered them impractical. Every passing day meant the object grew fainter, further away, and faster, and every lost night meant irreplaceable data slipping into the void. Yet the scramble was also a triumph of human ingenuity and global collaboration. Networks of telescopes were linked electronically to allow real-time sharing of images and measurements. Algorithms automatically flagged outliers in brightness and motion, alerting teams to sudden outbursts or unexpected behavior. Even minor discoveries, like a brief flare in activity, were communicated across continents, prompting immediate reallocation of observational resources to capture the event. It was a worldwide ballet of science, choreographed in real time against the backdrop of a rapidly disappearing visitor from another star. The speed and unpredictability of 3I Atlas also demanded flexibility in methodology. Traditional long-term monitoring projects were put on hold. Routine observations of distant galaxies or known asteroids were postponed or cancelled to make way for this one fleeting opportunity. Observers recalculated trajectories hourly, ensuring that telescopes remained pointed precisely at the moving target. The comet's rapid motion across the sky meant even minor errors could result in hours or days of lost data. Amateur observers contributed in unexpected ways, too. Equipped with modest telescopes but armed with determination, they reported brightness changes, tail morphology, and positional measurements, often providing coverage when major facilities were clouded out or temporarily offline. Their efforts created redundancy, reducing the risk of gaps in the observational record. In some cases, these contributions confirmed unusual activity first spotted by large observatories, reinforcing the collaborative nature of this global endeavor. Outbursts of brightness were particularly coveted. At times, 3I Atlas would erupt into spectacular displays, releasing massive clouds of gas and dust that illuminated its surroundings. These events were unpredictable, lasting only days or weeks before fading back to baseline levels. Each flare offered a rare glimpse into the inner workings of the comet, exposing volatile layers and revealing the processes at play in a frozen nucleus that had traveled across interstellar space. Missing such events would have been like failing to capture the opening lines of a centuries-old letter before it disintegrated. As the comet continued its inexorable approach towards solar conjunction, international coordination became more critical. Weather threatened observational efforts at key ground-based observatories. Storms, clouds, or dust could obscure data at the precise moment it was needed. Backup facilities in different hemispheres ensured that even if local conditions failed, another site could continue monitoring. It was a scientific insurance policy, protecting against the unpredictable while pursuing knowledge that could never be retrieved later. The challenge extended beyond optics. Infrared and radio observations required careful timing and calibration, as the instruments tracked both thermal emissions and chemical signatures. Spectroscopic data revealed the composition of gases and dust, providing clues about the object's origin, evolution, and activity. Every spectrum captured was a message from another star system, decoded in real time as astronomers raced to extract meaning from a fleeting visitor. This global campaign was as much about preparation as it was about execution. Teams had pre-planned strategies for data collection, software pipelines to handle real-time processing, and communication protocols to rapidly distribute critical findings. Every photon, every millisecond of exposure had to be leveraged. The event underscored a fundamental truth of modern astronomy. In the era of interstellar visitors, discovery alone is not enough. Rapid, coordinated response is essential to transform a fleeting glimpse into lasting knowledge. The urgency and success of this worldwide effort foreshadowed the next evolution in space exploration. Lessons learned from monitoring 3I Atlas are already informing the design of future missions, like dedicated interstellar interceptors that will not merely observe visitors, but chase them, study them in detail, and perhaps even return samples. Humanity's ability to mobilize across the globe, synchronize instruments, and extract data under extreme time pressure demonstrates that we are ready to move from passive observation to active engagement with the cosmic neighborhood. In the end, 3I Atlas reminded us that interstellar visitors are not distant, abstract concepts. They are tangible objects that arrive in our skies, fleeting but full of information. And while telescopes on 6 continents raced to keep up, the story of what lies within that icy nucleus continued to unfold, waiting for the next chapter in humanity's journey to understand its place in the galaxy. For centuries, humanity has gazed at the night sky as a passive observer, recording the motions of stars and the occasional wandering comet, but never truly interacting with the cosmic visitors that drifted into our solar system. 3I Atlas. Oumuamua, Borisov. These objects arrived like postcards from distant star systems, fleeting and untouchable, leaving us to decipher their messages through light alone. But what if, instead of waiting for these visitors to pass, we could meet them on their journey? What if we could reach out, touch their surfaces, and study them directly before they vanish forever? This is precisely the challenge that the European Space Agency has embraced with the Comet Interceptor mission. Unlike traditional spacecraft designed to chase predetermined targets, the Comet Interceptor is a master of patience and adaptability. It will not launch toward a specific comet. Instead, it will wait, silently stationed at the Sun-Earth L2 Lagrange point, a gravitational sweet spot where it can hover with minimal fuel expenditure, like a sentinel poised at the edge of the solar system. The moment a new interstellar visitor is discovered, this spacecraft will spring into action. Calculations performed in real time will determine the optimal trajectory, and the Comet Interceptor will accelerate toward its target, reaching speeds that allow it to catch up with objects traveling hundreds of thousands of miles per hour. The technology required to accomplish this is staggering. The spacecraft must remain dormant, fully functional, and ready to respond on a moment's notice, potentially years after launch, while carrying enough fuel and maneuvering capacity to reach an object whose properties remain entirely unknown. Designing instruments for such an unpredictable encounter presents its own challenges. Scientists must anticipate everything from tiny rocky interlopers to enormous active comets, ensuring that cameras, spectrometers, dust analyzers, and magnetic field sensors are versatile enough to capture meaningful data under any circumstance. Every gram of mass is precious, balanced against propulsion requirements and the complex orbital maneuvers needed to intercept a target traveling at extraordinary velocity. It is a mission defined by extremes: extreme precision, extreme speed, and extreme flexibility. The conceptual elegance of Comet Interceptor lies in its proactive philosophy. Historically, our understanding of interstellar visitors has been shaped entirely by what we can observe from a distance. Telescopes capture light reflected or emitted from these objects, revealing hints of chemical composition, activity, and structure. Yet much remains hidden, locked away beneath surfaces preserved for millions of years. By meeting a visitor in person, the spacecraft can probe interior layers, detect volatile emissions, analyze surface chemistry, and even study dust particles streaming from the nucleus in unprecedented detail. Imagine for a moment approaching a cosmic time capsule that has traveled across light years of space. The spacecraft will fly alongside the visitor, instruments scanning and analyzing every feature. High-resolution cameras will map its terrain, cracks, ridges, jets of gas, and frozen dust structures. Spectrometers will decode isotopic ratios, revealing clues about the temperature, pressure, and chemical environment where the object formed. Dust analyzers will capture tiny grains that drift from the surface, frozen witnesses of a star system far removed from our own. Every measurement will transform the abstract into the tangible, turning points of light in the night sky into physical evidence of alien planetary systems. The Comet Interceptor mission also introduces a paradigm shift in how humanity interacts with space. Instead of chasing targets after discovery, scientists are designing a system that anticipates chance encounters. It is a philosophy akin to a wildlife biologist positioning themselves along a migratory corridor, ready to study a rare species as it passes by. The goal is not merely observation, but engagement, active participation in the journey of objects that have traversed the galaxy long before Earth was ready to receive them. The challenges are enormous. Interstellar objects are fast, unpredictable, and often small. Their surfaces may be fragile, their compositions unknown, and their trajectories difficult to refine in the limited window between discovery and closest approach. Navigational calculations must account for every nuance of solar gravity, the subtle push of radiation pressure, and the unpredictable effects of outgassing. Every second of delay can mean missing the target entirely. Yet the potential rewards are staggering. With a successful intercept, scientists will gain direct access to materials that formed around stars other than our Sun, samples of alien water ice, carbon compounds, and metals that have been preserved in deep freeze for millions or even billions of years. The data will provide a new benchmark for models of planetary formation, stellar evolution, and the chemical diversity of the galaxy. We may finally answer questions that telescopes alone can only hint at. How common are complex organics in interstellar space? Do alien comets carry the building blocks of life? How do planetary systems eject debris into the vast highways of the Milky Way? The Comet Interceptor concept also reflects a broader transformation in astronomy and space science. Humanity is learning to anticipate rather than merely react. Automated sky surveys now monitor vast swaths of the heavens every night, identifying moving objects as faint as a few kilometers across. Artificial intelligence analyzes the torrent of data in real time, flagging unusual trajectories that might signal an interstellar origin. And when the next visitor appears, we will not wait helplessly for it to vanish. We will meet it, study it, and perhaps even carry fragments back to Earth for detailed laboratory analysis. In many ways, the mission embodies a philosophical leap. For centuries, humans have considered the stars as distant, untouchable, and beyond direct influence. Now, with the Comet Interceptor, we are actively reaching out, intercepting messages written in ice and rock and translating them into knowledge. We are no longer passive observers of the galaxy's story. We are participants, turning fleeting cosmic whispers into chapters of understanding that will last for generations. The vision extends beyond a single encounter. Lessons learned from the Comet Interceptor will guide future missions, inspire more sophisticated spacecraft capable of rendezvous or sample return, and open the possibility of systematic exploration of interstellar debris. One day, we may develop fleets of agile interceptors, poised at gravitational waypoints throughout the solar system, ready to meet and study every visitor that crosses our path. As the mission awaits its first target, the universe continues its endless dance. Somewhere in the vast reaches of the Milky Way, fragments of distant star systems hurtle along invisible highways, carrying chemical messages, physical relics, and clues to the diversity of planetary formation. When the next interstellar traveler arrives, humanity will be ready, not just to watch, but to reach out, touch, and understand. Across the seemingly empty expanse of the Milky Way, stars appear solitary, scattered like distant pinpricks of light. Yet beneath this tranquil facade lies a hidden network of motion and momentum, a vast system of gravitational currents threading through the galaxy, guiding the paths of objects that have been ejected from their home systems. These are the invisible highways along which interstellar travelers like Oumuamua, Borisov, and 3I Atlas glide, carrying with them stories from worlds far beyond our own. Astronomers have long suspected that interstellar objects do not drift randomly. The galaxy's gravity, shaped by the collective mass of billions of stars, along with the movement of star clusters and the tidal pull of galactic arms, creates pathways that shepherd wandering debris across vast distances. Computer simulations of galactic dynamics have begun to reveal these hidden roads, curved trajectories that link stellar neighborhoods and funnel ejected material along predictable routes. It is as if the Milky Way is a city, and these objects are vehicles traveling along thoroughfares dictated by the subtle pull of invisible forces. Simulations show that when a planetary system ejects debris, whether from violent collisions, gravitational nudges from massive planets, or the explosive end of a star, these fragments do not scatter in every direction. Instead, their fates are shaped by the collective gravitational landscape of the galaxy. Some fragments enter long, looping paths that weave through multiple star systems before encountering another. Others follow tighter corridors that keep them confined within particular galactic regions, increasing the likelihood that their journeys will intersect with stars like our own. Understanding these cosmic roads allows astronomers to do more than merely watch these visitors arrive. It opens the possibility of predicting the near appearance. By combining simulations of galactic dynamics with precise measurements of stellar motions, researchers can identify regions of the sky more likely to harbor inbound interstellar travelers. Certain binary star systems, for example, generate particularly complex gravitational fields that act like launch pads, sending objects careening outward with enough velocity to escape their home star and join the interstellar traffic. Stellar nurseries, dense clouds of young stars, also produce concentrated streams of ejected material, forming routes that wind outward across the galactic plane. Think of this effort like mapping a highway system without ever seeing the roads directly. Astronomers rely on the positions, velocities, and trajectories of stars to model the gravitational terrain. Then, by simulating how objects would move under these influences over millions of years, they can trace potential pathways that connect one stellar neighborhood to another. The resulting maps reveal that our solar system sits at the intersection of several of these cosmic thoroughfares, which explains why we have now observed multiple interstellar visitors in such a short span of time. Far from being a random fluke, these arrivals are the natural consequence of the Milky Way's hidden infrastructure. The predictive power of these simulations is profound. By knowing where these gravitational roads intersect with our solar system, astronomers can position survey telescopes to monitor the most promising regions. Automated sky surveys, such as Atlas, Pan-STARRS, and the upcoming Vera Rubin Observatory, can then scan these corridors night after night, searching for faint streaks of light that indicate a fast-moving visitor. By focusing attention on likely routes, scientists increase the probability of detecting new interstellar objects before they pass beyond reach, transforming DISCO vary from serendipity into strategy. Moreover, these maps provide critical insights into the origins of the objects themselves. A fragment traveling along a particular corridor may carry chemical fingerprints pointing to a specific type of star system, perhaps one rich in metals, or a binary pair with powerful gravitational interactions capable of ejecting large debris. By combining trajectory predictions with spectroscopic observations, astronomers can begin to reconstruct the life stories of these cosmic travelers, tracing their paths from distant cradles of planet formation to their brief appearances in our night sky. The work also underscores the interconnectedness of our galaxy. Every star system is not an isolated island, but a participant in a vast, dynamic network. Material that leaves one system can, given the right trajectory and velocity, find its way into another, carrying frozen records of distant worlds across light years of space. These invisible highways are nature's channels of chemical and physical exchange, connecting stellar neighborhoods and challenging our perception of galactic solitude. In practical terms, mapping these highways requires massive computational power. Simulations must track not only the gravity of individual stars, but also the cumulative pull of stellar clusters, molecular clouds, and the Milky Way's spiral arms. Timescales stretch over millions of years, and small perturbations can dramatically alter the paths of ejected objects. Even the subtle push of radiation from nearby stars or encounters with interstellar gas can influence trajectories. Yet despite the complexity, patterns emerge. Corridors of increased object density, regions where interstellar debris tends to cluster, and predictable intersections with the solar system where we are most likely to observe new arrivals. This knowledge is already changing how astronomers plan observational campaigns, survey. Strategies are shifting from blanket coverage of the sky to targeted monitoring of likely approach vectors. International collaboration ensures that telescopes spread across the globe can respond quickly, providing continuous observation of any newly discovered interstellar visitor. By integrating predictive models with real-time detection, humanity is beginning to anticipate the arrival of cosmic messengers instead of waiting passively for chance encounters. Beyond the practical benefits of discovery, mapping galactic highways reshapes our understanding of the Milky Way itself. It reveals a galaxy not as a static backdrop of stars, but as a living, moving system with its own currents, lanes, and patterns. Each interstellar object becomes a traveler along these lanes, a physical witness to the invisible structure of our cosmic neighborhood. By decoding their journeys, we learn not only about the objects themselves, but also about the gravitational architecture of the galaxy, the mechanisms that eject material from distant star systems, and the hidden order underlying what once seemed like chaotic motion. And so, as we map these celestial corridors, we open the door to a new era of interstellar anticipation. Each predicted pathway, each gravitational road, brings us closer to catching the next cosmic messenger, to analyzing its chemical secrets, and to understanding the interwoven network that connects distant stars. We are learning to navigate the galaxy, not with ships or rockets, but through knowledge, computation, and vision. The discovery of interstellar highways reminds us that the galaxy is a place of constant motion and exchange, where our solar system is but a single junction in a complex web of paths traveled by countless wandering objects. By studying these trajectories, we not only prepare for future encounters, but also gain perspective on our place within the Milky Way's vast, interconnected tapestry. As astronomers refine their maps and simulations, one question looms: what will the next visitor carry with it? And how much more can we uncover about the secrets of distant star systems before these cosmic travelers vanish once again into the depths of space? In the grand expanse of the cosmos, Most of our knowledge comes from light, the glow of distant stars, the faint infrared signature of exoplanets, the shifting patterns of cosmic dust. All of these serve as our primary sources of information about worlds far beyond our reach. Yet interstellar objects like Oumuamua, Borisov, and 3I Atlas offer something far rarer: direct access to matter forged in alien star systems. These cosmic visitors are physical samples, time capsules that carry frozen histories across unimaginable distances. For the first time, humanity can touch the material of another world, analyze it, and begin to piece together the life stories of distant stellar neighborhoods. The chemistry embedded in these visitors is like a message written in atoms. Water isotopes hint at the temperature and pressure conditions of their birthplaces. Carbon compounds, from simple carbon monoxide to complex organic molecules, reveal the environments where chemistry was free to evolve and combine over millions of years. Heavy metals and isotopic ratios tell tales of stars that lived and died long before our sun even formed. Every particle is a fragment of a larger story, one that extends our understanding of how planetary systems develop, how they mature, and how they exchange material with the galaxy around them. These objects are more than just chemical curiosities. They demonstrate that our galaxy is not a collection of isolated solar systems, but a dynamic community linked by invisible highways. Interstellar debris travels along predictable gravitational corridors, connecting distant stars, carrying matter and information across vast cosmic distances. When we detect a new visitor, we are seeing a thread in this galactic web, a tangible sign of interstellar interaction that has been occurring for millions of years. The implications for planetary science are profound. By comparing the composition of these visitors with our own solar system's comets and asteroids, we can test theories of planet formation under entirely different conditions. We can observe the range of chemical diversity produced in other systems, assess how common certain molecules are, and investigate whether processes like complex organic synthesis, essential to the development of life, occur universally or only under specific circumstances. Each visitor adds a new data point, a new piece of the puzzle that challenges or confirms our assumptions about how planetary systems evolve. The emergence of interstellar archaeology represents a paradigm shift in human exploration. Previously, astronomy was largely a study of light, indirect, interpretive, reliant on photons traveling across years of space and time. Now, we have the potential to analyze material directly, to conduct laboratory experiments on matter that originated around a star we will likely never see up close. It is the difference between looking at a distant city through a telescope and walking its streets, examining its architecture, studying its culture firsthand. Even more, interstellar archaeology invites us to reconsider our place in the galaxy. We are no longer just inhabitants of a single solar system. We are part of a broader community connected through the exchange of matter and energy. Every fragment of ice, every speck of rock that passes through our neighborhood is evidence of this ongoing dialogue between star systems. The Milky Way becomes less a backdrop of isolation and more a networked, interactive environment where stars, planets, and debris all play a part in a living, evolving ecosystem. Future missions promise to deepen this understanding. Spacecraft designed to intercept incoming interstellar objects could perform high-resolution analysis, return samples to Earth, or even deploy instruments directly onto these bodies. The next visitor may carry material unlike anything we have encountered, clues to exotic chemistries, novel isotopic ratios, or complex organics that expand the known possibilities of cosmic evolution. By positioning ourselves along these predicted cosmic corridors, humanity can transition from passive observation to active participation in interstellar science. At the same time, the study of these visitors challenges us to think on unprecedented timescales. These objects began their journeys long before the Earth even formed, preserving conditions from eras and environments that no longer exist. They are snapshots of distant stellar histories, frozen in ice and rock, traveling across millions of years to arrive in our instruments and observatories. Through them, we gain not only knowledge of alien worlds, but perspective on our own place in the galaxy's deep temporal and spatial web. Each interstellar arrival reshapes our understanding. Oumuamua taught us that small, inert objects could traverse space in ways we had not anticipated. Borisov confirmed that comets from other systems behave similarly to our own, yet carry subtly distinct chemical fingerprints. 3I Atlas, with its immense size and spectacular activity, has expanded the spectrum of possibilities, challenging our assumptions about what types of objects can survive the journey between stars. Collectively, they reveal a galaxy richer, more connected, and more complex than we ever imagined. In this new era, every interstellar visitor becomes both a scientific opportunity and a cosmic messenger. Their passage reminds us that the universe is vast, dynamic, and full of surprise. They carry the histories of stars long gone, the chemical tales of distant planetary systems, and perhaps even the building blocks of life itself. As we continue to detect, track, and study these objects, we are effectively reading messages from across the galaxy, letters written in ice, rock, and dust, addressed to the curious minds of humanity. The dawn of interstellar archaeology is just beginning. It is a discipline that blends astronomy, chemistry, planetary science, and even mission engineering, demanding rapid response, global collaboration, and imaginative thinking. It invites us to look beyond the confines of our solar system and consider our role in a galaxy that is not empty, but alive with motion, exchange, and connection. And as each new visitor arrives, we are reminded that the universe is not a distant backdrop, but a participant in our story. These cosmic travelers, fleeting though they may be, offer enduring lessons that the Milky Way is a network of relationships, that planetary systems are diverse and dynamic, and that humanity's curiosity and ingenuity are capable of reaching across light years to uncover the secrets of worlds beyond our own. The next chapter of our journey, literally and metaphorically, lies in the arrivals yet to come. Somewhere out there, along the invisible highways of the galaxy, the next messenger is already on its way, carrying new stories, new mysteries, and new opportunities to redefine our understanding of the cosmos. And when it arrives, we will be ready to meet it.